and STIs. Those cars with 300 plus horsepower and the computer control yoke, computerized yoke control, distributing the forces all evenly and to make sure you have all traction and stuff like that, is worth nothing. In fact, it's negative in the case of autocross. Because in autocross, you're approaching one corner to the next one in such a small, short amount of time. By the time the computer responds to the first cornering, you're already at the second corner. And your turbo, right after it has spooled up, it's time to stop again. It's time to brake the car. So it's totally worthless in autocross, when you have those 300 plus horsepower and all-wheel drive and all that crap. People go for simple in autocross because, occasionally, not so occasionally, you will run into cones. You don't want to get your $30,000 plus car to get coned. The worst part is when you're not just hitting over and knocking over a cone. The worst thing is when you have the cone under your car, right under the catalytic converter. Oh. Yeah, that would be bad. Then your car will stink for weeks because of all that plastic. Alrighty. So let's go ahead and talk about your next homework assignment, because I'm pretty sure some of you are just waiting and dying to see what is the next homework assignment. It's called a music box. Okay. So before we talk about the homework assignment, I'll just kind of quickly introduce what a real music box is, because I know most of you know what a music box is, but because we are in the information age, everything is digital and stuff like that. Many people have only seen a picture of a music box, or have an app that looks like or act like a music box, instead of having actually seen a real music box. So we'll just look at what is a music box first, and there are plenty of videos on music boxes. We'll pick one. That actually shows the mechanism. That would be a good one. Hold on a second. Let me get the sound working here. Okay, I guess they're all hooked up to my speaker, and then we'll check the audio channel. We should be recording as well, so I better double check that too. So the recording part is good. Output devices. Let's see. Let's play this, and I'll figure out which one it's supposed to be. Okay. Nope. Okay, so let's look at output devices and make sure it's not muted. There we go. All right.
Secret to the music box is the comb. I'm sure you've done this many times before. Flicked the teeth of a comb and made music. You've probably noticed that the longer teeth give you a deeper note, and the shorter teeth a higher note. Maybe you've even tried to play a tune on a comb. I'll try Three Blind Mice. Only very approximately Three Blind Mice. Trouble is, it's much more difficult than playing the notes on a piano, because you're not sure which tooth you should pluck next. You have to approximate. If we could see a single tooth from a comb, it would be a bit like looking at a hacksaw blade. Watch this when I flick the hacksaw blade poking over the end of the table. It vibrates. Not only does it vibrate, but you can hear a note, very deep note in this case, because it's making the air vibrate, which makes your eardrum vibrate, and that's why you hear sound. What if we make the vibrating part of the hacksaw blade shorter? Watch this. Make it shorter. You guessed it, the note is higher. You can even shorten the vibrating blade as it's vibrating, and you get a wonderfully strange effect. Watch this. Great fun to play with. Well, if you had a whole lot of hacksaw blades, maybe you could set up a comb made of hacksaw blades. I've done that here. Have a look. There we are, 6 hacksaw blades.
It's getting to where we need
them so that different amounts poke over the edge of the table. Now, I'll place a couple of pieces of cardboard over the top, very carefully, and then hold the cardboard in place by means of a ruler, pressed down firmly. And now we should be able to make sure that only the bits poking over the edge vibrate. Start with a long one, fairly deep note, and as they get shorter, the hacksaw blades give progressively higher notes. Well, let's try once again, Three Blind Mice. Well, it's not perfect, but it's getting closer. If you want to make your own little musical instrument out of hacksaw blades, you can actually compare the notes on a piano, and when they're absolutely perfect and you're happy with them, hammer them in place onto a block of wood, and you'll have your very own hacksaw blade instrument. What has this got to do with a music box? Surely there are not hacksaw blades in a music box. No, but there is a comb inside the music box, and here's one which I've removed from a music box. Have a look at that. You can see that there are metal teeth and they vary in length. Now I wonder if you can guess which ones will give us high notes and which ones will give us low notes. Very easy from what you know now, isn't it? The longer teeth give you lower notes. The shorter teeth, high notes. But it's very difficult to play, even with a wooden skewer. What happens in the music box is that little comb is attached to a metal block usually, in this case by 2 screws, and there's a little drum which has lots of little knobs on it, and those knobs will actually pluck the teeth when you turn the handle. Well, here's one that's been put back together. There it is there. And if I wind the handle, see if you can recognise the tune. You can not only recognise the tune, but you can also see the teeth being plucked. Now, 2 things are needed for a music box: the comb and the program, or the little knobs, in this case on a drum. There is a 3rd thing needed. See if you can guess what it is. I'll pick it up and go on playing. And you can hardly hear the tune, because the 3rd thing, something to vibrate, is missing. It doesn't have to be the tabletop, which it was to begin with. It could be something like a glass. And in that case, the glass is actually vibrating. Or something as simple as an old empty cardboard box. It's acting as the resonating box. Well, what about the original music box? Does that have anything at all like that inside? Let's have a look. Wind it up, because it has a clockwork motor. Open it up and have a look at that. Almost identical to the one we just looked at. There's the comb, there's the drum with the knobs on it, that's the program, and down there is the clockwork motor with a spring inside it and a handle on the back. So all those are in position. Music boxes are very old. Some of them have been around for hundreds of years, and we have one here which was made in Germany over 100 years ago, and it's called a polyphone. It used metal discs with hundreds of slots in and little bumps on the back. And the music box itself was made of beautiful inlaid polished timber and brass fittings. There it is, the polyphone. Now inside it contains some of the things you'd expect of a music box. A metal comb and little hammers that actually plucked the teeth of the comb. And also it had a clockwork motor, and the box itself was the resonating chamber. Now the cunning thing about this music box is that you could get different discs for it, and each disc was a program for a different tune.
Different apps.
We want to play this tune. All we do is drop the disc in position, lock it in place, wind up the clockwork motor, pull out a little lever, and you listen to your favourite tune.
Hey, they never warned me about nudity.
So part of my retardation, but so the rickets on the disc are acting as what?
I think that controls which part gets plugged.
The hammer.
Yeah. Okay. So the next question is, what does this have anything to do with your homework assignment or this class in general? Well, guess what? Inside the processor, is a music box mechanism. Okay? The reason why there's a music box is, okay, what have we talked about so far? We talked about two really important things that have to be there inside a processor. Okay? One is the adder and the subtractor, right? Now, technically, you can also make multipliers and dividers and stuff like that, as circuits, okay? But, we start with the adder and the subtractor. Those are the most elemental computation mechanisms. We also have registers, okay? Registers are things that are inside the processor that can remember things, okay? Like, numbers that you have just added, okay? So they can use those numbers again to make a running sum and stuff like that. But something has to tie everything together, okay? Something has to say, okay, I want this register, but not that register. I want these registers to go to the subtractor, and then take the output and put it back into that other third register, and so on. Something has to be doing the coordination. And from the previous class, we also learned that in order to use registers, we have to plug the clock line, right? Mm-hmm. Because the low to high transition is what is going to make a register update its internal content. Are we okay with all of that stuff so far? Okay. So some kind of central mechanism has to be coordinating all of these things. And for the most part, these coordinations is very mechanical. Okay. It's like, okay, do this, then do this, then do this, then do this, and then do this. Okay. So does that resemble anything that the drum of a music box can do? Mm-hmm. Yep.
The spring turning the system automatically?
The spring that is turning the system, which we don't use a spring because we don't want it to run out.
Right.
So we have a mechanism that is kind of perpetuating. Okay, but it has the same mechanism. It is something that propels, something that turns. Okay. So what we're going to do with the homework assignment is to start on this process. Okay, so your homework assignment for this class, for the next week, is a music box. Except we don't make music out of this music box. But we do something kind of fun with it too. Let's see, where's my assignment? This is okay. So the music box is the most basic form of automation. It's kind of like a macro, a really dumb macro, okay? You say this, and it would just keep playing the same tune over and over again. You say that, it would just play another tune. But it is the most basic form of automation. Okay, I want a sequence of zeros and ones, going to different control lines. This is it. Okay, but the other control lines the processor has to deal with include the control lines going to memory. Remember how we work with memory? You have to put out the address, and then you have to control the read-write line, or they call it the load line. And then the memory chip has its enable chip, okay, chip select line. It also has an extra line if you're dealing with RAM. There's also a line to control, okay, when do we store the content into the memory? So all of these things require coordination, and the music box drum mechanism is an analogy to do that, to get it done. So instead of plucking the comb or individual, how do they call it, teeth of a comb, instead of plucking that, we're plucking lines that can either be a 0 or 1. Okay, so that's what your music box is doing. Is it's plucking these lines, that can turn a line to 1 or 0. So that is the why. Okay, because it is relevant to the internal working of a processor. So the what here is what are we going to do with this homework assignment? The homework assignment basically is a self-playing mechanism that basically replaces the content of some kind of memory over and over again. So what we're going to do is we're going to use a ROM, a read-only memory, as one of the components so that the con does not get reset upon power resetting, okay? Because we want this mechanism to keep working as long as it is powered up. In LogicSim, all it takes to run the music box is to enter simulation mode and have a clock tick at a certain frequency and watch the mechanism works. Are there any questions about the what? So we're making quote-unquote a music box that really does not play music, but it has something that is visual, and it keeps doing that over and over again. Okay? All right. I can just use LEDs, make a sequence and stuff like that, but we're going to make it more fun. The music box has two components. The memory, or the ROM, stores the pattern that is to be replayed. Each location or each memory location of the ROM corresponds to what to output at a particular slice of time. In other words, when you look at the drum, okay, so when you look at the drum of a music box, And if you look at it horizontally, in this case, each slice horizontally becomes a memory location. Okay, so by programming the individual bits of your ROM, you're now controlling what to play at what time, in what sequence. Are we doing okay so far with that? Okay, all right. And you get to control the width of the data bus, because what the width of the data bus is equivalent to is the length of the drum in the case of a music box. The longer the drum, the more things you can plug in, the more things you can control. So you can basically determine how wide you want the data bus to be, because that determines how many things you have to control, you potentially control at the same time. The address bus or the address port of your ROM is also under your control. You get to decide how many bits you want to allocate to the address port. The address port is corresponding to the diameter of the drum. The bigger the diameter, the more complex song it can play, because the longer the sequence. Okay, the shorter the diameter, the fewer the slices you can have on the drum, and as a result, the music piece you can play will be simpler. So the one that we're dealing with is really, really simple. So I think most of you can kind of determine what is the correct size for the address port. Okay. Another main component of is a counter that increments a clock tick. In other words, there's one thing that controls, which slice of the drum are we looking at? The rotation mechanism, so to speak. Okay, and we have just the mechanism to do that. We attempted to do that in the previous class or during the lab time. If you missed the lab, you can watch the video again. Okay, but in the lab we talked about a mechanism by combining an adder and a register to make that kind of self-turning mechanism. Okay, but it needs a clock, right? The clock is basically the handle on the music box that you crank, so that every time you crank the handle or every time you change the state of the clock, it advances the rotation of the drum. Okay, so that's what we want to do. So a counter can be implemented using a register and an adder. Okay, so in this case, you don't have to implement your own adder. You can just pull an adder out of the library and plug it into your design. Okay, and then some extra circuit components. So to make a music box like this as a homework assignment, you will need only these components. Okay, so do not use anything other than these components. You will need one ROM component. Well, that's kind of obvious because that is the drum of your music box. You will need one register and an adder. Okay, so these two combined, okay, let me just highlight both of them. So these two combined becomes the mechanism to advance the drum. The drum itself is the ROM, okay, but the gearing and also the mechanism to advance and turn the drum composes of the register as well as the adder. Okay? And then you need a clock line. A clock line is not an input pin. You can initially, when you test your design, you can just use an input pin if you want to, but there are ways to use a clock line and be able to single step the clock line. Okay, I'll show you guys how to do all that stuff in just a little bit. Okay? And the difference between a clock and an input pin is in simulation mode, okay, when you're actually testing a design, a clock line enables automated toggling. In other words, you just say, I want to toggle this at 5 Hertz. Then it will be toggling 5 times per second automatically. As opposed to an input pin where you have to click it in order to change the state. So I want you guys to use the clock line because I don't want to have to keep clicking the mouse when I'm grading this homework assignment. I want to just say run and then watch it go. Okay? You also will have one 7-segment display, which many of you do not know. What is that? Okay? Because these days we do not use 7-segment displays much, except on, no, we don't even use these on the billboards or other things. We have dot matrix, HD TV and stuff like that. We don't need those stinking 7-segment display. A 7-segment display, I'll show you guys what it is later on, and also how to use it.
You play with like Arduinos.
If you play with Arduinos, that becomes really useful because it's very easy to control, and yet it is very effective if you just want to display numbers, including hexadecimal numbers. You will have a button. So once again, a button is not an input pin. It is kind of, it looks like an input pin, but it's not, because a button is, if you don't click it, it has a normal state, has a default state. When you click it, then then it will change the state. But the moment you release it, it goes back to the original state. It's a push button concept. Yep.
Is it like saying the counter can only go up, and once it reaches its max, you have to reset it in order for it to continue?
It is described here. Okay, so there's a description of what it's supposed to do. But that's a good question. You will need an OR gate. Okay, this is used so that we can merge two ways to reset the counter to a single reset signal. You need a splitter, so you can split the output of the ROM into individual wires. Okay, and where those wires are supposed to go, you have to figure out. You will probably need two constants, okay, to get this design to work. One constant, but both of these constants have to go to the adder, because you need to make sure that you're only adding a particular number to the number that is already in the register. And to do that, you need two registers, because I don't want any input pins left unconnected. Output pins, okay, if you don't find the use of the carry out from the adder, don't hook it up to anything. But as far as input pins are concerned, I want every single input pin to be connected. Because if you remember from the discussion several classes ago, if you leave input pins unconnected, the input pin will still try to interpret the voltage at the pin, but then the voltage at the pin is now depending on what is interfering with the line leading to the pin. In other words, it's just random stuff, and you don't want that to happen with an actual circuit. So we don't want any design like that in our class either, to have unconnected input pins. You can use any number of wires. Okay, so as far as wires are concerned, you can do whatever you want with the wires. So the music box, quote unquote music box, only needs to display A to F. I thought I changed that. Is this the right class? Nope, it's the wrong class. Okay. I restored another class, so it's actually the wrong one. This is the right one. It's very much the same, so don't worry, I didn't change a whole lot. But there are some minor differences between your version and the one version that the other class did. Okay. So everything up to here is the same, except in your case you have to display the digits from 0 to 9 instead of A to F. You have to do it repeatedly when the tick is enabled in simulation mode. Do not light up segments that are not a part of the digit. Okay, so I don't want the period of a segment display to light up when because I did not ask for that particular dot to be lit. I'll show you guys what it means when we get to the explanation part of the individual components. For testing purposes, choose a low tick frequency so you can actually see what is going on. You may also want to enable logging so that you can analyze the behavior of your design for debugging purposes. So I'll talk about all of these mechanisms in LogicSim when we get to LogicSim. Note that each digit should be displayed for exactly one clock tick cycle. So I don't want any one of the digits to display less than or more than one clock tick cycle. The tricky part of the design is the number of locations in ROM is a power of 2, because that is determined by the width of the data port. If your data port has a width of 3, it means you have 8 locations, because 2 to the power of 3 is 8. If you choose to have 4 bits as the width of the address port, then you have 16 locations, because 2 to the power of 4 is 16. Okay, and you notice that 10 is not exactly a power of 2, so you would have to figure out a way so that you can cycle things. Okay. Note that each digit should be displayed for exactly one clock cycle and move on to the next digit. Moving on to the next digit should not require any user intervention once the tick is enabled. So you need to figure out a way so that when the first 10 locations of the ROM are cycled through, the counter needs to be automatically reset to the first location. And you cannot use any additional components other than the ones that I have listed. Okay?
We're allowed to use gates.
Hmm?
Were you allowed to use any kind of gate logic?
You're allowed to use one OR gate.
One or
Just one OR gate. No negated input or output. So make sure no input is left unconnected. I mentioned this a little bit earlier. And this is just how you turn in a homework assignment. You want to save your logic sim file as musicbox case sensitive .circ. And you also want to save your ROM file, okay, because you want to attach those two files together. Make a zip file out of those two and call that musicbox.zip and turn that zip file in. So are there any questions about what the music box is supposed to do and how and what to turn in for this particular homework assignment? No questions? Okay, so we'll go to LogicSim now and then take a look at all these different individual components, and you guys can ask questions when we get to that part. So let me open it here. LogicSim is still in the downloads folder, I think. There we go.
So you want us to loop through 10 locations in ROM?
Yep. So the output of your LED display, the 7-segment display, should be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 0, 1, 2, 3, 4, 5, 6. So it has to go in circles.
And reset once it hits?
Yes, but it should not require the end user to have to press anything to reset. But the end user can press the reset button to manually reset it.
Oh, okay.
Yeah, so there are two ways to reset. Huh?
If it's at 6, it should go back.
Right, when you press the button. Right. Okay, so I'll go ahead and show you guys all the individual parts that you have to use in this particular design. Okay, here's a splitter. Okay, splitter is pretty clear. What it does, it splits a multi-wire line into multiple lines. You will need you don't need a pin anymore. Okay, what you do need is a clock. So this is a clock which looks like an input pin, but it's not, because it has that little clock cycle thing as an icon inside. So the difference between this and an input pin is this can be automatic. The clicking or the ticking, I should say, of a clock, it can be automated in simulation mode, whereas an input pin cannot. You will need two constants of any width that you choose to use, okay, and any constant that you want to use. Let's see, those are the ones that we need to use here. And then over here, you need an OR gate that only has 2 inputs. Okay, so you need an OR gate. That's the only gate that we need. In terms of arithmetic, we need an adder. And once again, the width of the adder you have to choose. Okay, so you have to choose the data bits of your adder. And then you need a register. So down here we will use a register. Now remember, a register is really just a multi-bit edge-sensitive D flip-flop that we talked about last time. Okay, now this one has a little bit more control lines because it is a fully implemented one. So I will talk about the actual individual ports of this thing. That's the only memory. Oh, there's also a ROM component. So once again, you have to determine the number of bits for the address port as well as the number of bits for the data port. Okay, the select, you can basically say it's always on. Okay, and you can reuse one of the constants to make it always on. Okay, because one of the constants can be connected to both the adder and also the ROM. Okay, and then when it comes to input output, this is where the fun begins, because we can pick a 7-segment display like that in your design. So these are the individual components in your tray as you try to put them together to do whatever the homework assignment is asking you to do. So what I'll do today, right now, is to demonstrate just how to make use of each component. Okay. And also, you can look up the library reference. So you can look up the library reference and look at the 7-segment display. Okay, if you just look up the 7-segment display, it will show you the behavior is to display the values of the 8 1-bit inputs. Segments are either colored or light gray depending on the input. The corresponding is as follows. So I'm not sure whether you guys can see the little wires from the pins into the segments. I'll just kind of point out one that is kind of obvious. Like this one here, if you look at the one that is at the lower left corner, the pin here, it connects to this particular segment. So a 1 on this pin lights up this segment. A 0 on this pin will turn it into dark. So that's basically what it is. So each segment, including the period here, has its own pin connected to it. It's a 7-segment display plus the period. So there are 8 input pins.
0 through 7.
Take it?
0 through 7.
0 through 7.
These are the line, as far as, if you were talking about an array, what would be the index?
Right, the indexes would be from 0 to 7, but since the pins are not indexed in any way, so they're just, we just say there are 8 pins as inputs. Are there any questions about the pins to to a 7-segment display?
And display shows 0 through 9.
I wanted to show 0 to 9, but you can only control, so at the very basic level, okay, I'll just show you how to make one segment light up. Bing!
Oh.
If you want another segment to light up, bing! And if you want another segment to light up, I just pick this one here, and so on.
And
Okay?
you said don't worry about the period.
No, do not make the period light up because it's not supposed to. It's not a part of a digit. Okay? So individually, this is how you use a 7-segment display. A 1 to a pin lights up a particular segment in the display itself. But the mapping between the pins and the segment is in the library reference, so you can just read that and figure out how to, okay, a 1 is going to have these bits, a 2 is going to have these bits. Go ahead.
Can you just leave the period disconnected, or does that kind of?
It's an input pin.
So
Yep.
we can't use a constant to keep the period turned off.
Well, if you figure out a way to use the constants that are already in the system, so go ahead. There are ways to do it, yes. But you can also just use 1 bit from the output of the ROM to control that. It's just that that bit is always 0. Okay? Question? No? Okay. So are we good with this design so far? Okay, so I want to show you, how the clock pin works. So I'm going to show you the clock pin and just go around and make it control a particular thing here, okay? And since it is a 0 at this point, the pin that this controls, let me look up the library reference. So we are talking about this pin here. It is controlling the top bar of the second.
Center.
Oh, the center. Okay, good. Thank you. So it's controlling the center, and it is not lit at this point because the clock line is a 0 at this point. But when you go to simulate mode and you say tick enabled, okay, let's pick a frequency first. So the default frequency of ticking is only at 1 Hertz, which is 1 cycle per second, which is definitely, we can see that, okay? But at this point, even though simulation is enabled, I did not have tick enabled, and that's why it's not ticking. For debugging purposes, you might want to use Control T, which is tick once, okay? So that would make it 1 state transition at a time. So let me just do that here, okay? Control T on the keyboard, okay? Control T again on the keyboard, Control T again. So a clock line is one that can basically cycle between 0 and 1 automatically. Now when you're bored with this, then you can just say ticks enabled. Then the design will take all by itself, just like that. So basically when your design is all done, the display should go from 0 to 9 and then go back to 0 and then go back to 9 all the way. So you would just keep cycling all the numbers from 0 to 9 and then go back to 0 again. Are we okay with that concept? Yes? Okay. All right. So any other component that you want me to explain other than the register, because the register is kind of like the D flip-flop that we talked about the other day, except that it has 1 extra pin that we haven't talked about. Yep.
Just to confirm, the adder you gave us works exactly like the adder we actually created.
Yes.
Okay.
So the adder has exactly the same kind of input. You're adding 2 numbers, okay? So these 2 on the left edge, these 2 ports are the numbers that you're adding. The top pin is carry in, the bottom pin is carry out, and then the pin on the right hand side is the output number. Now the input and the output ports, they all have the same width. So you will have to decide, okay, what is the width that I need for the adder? Okay. Any questions about how to use the adder? Remember, I don't want any input pins to be unconnected. Yes.
I have a question. How to transcode binary code to 7-segment display?
You look at the picture, and then you figure out which pin needs to be a 1, which pin needs to be a 0.
Yes, but binary code, how it corresponds to, for example, how to do like 1 in binary and 2 in binary and make it looks like 1 and 2 in the display.
Well, you have to figure out, okay, so let's say I want this to look like an E because I don't want to do your homework, right? Okay, so an E is going to light up this segment, this segment, this segment, this segment, and also this segment. So I need this pin to be a 1, I need this pin to be a 1, I need this pin to be a 1, I will need this pin to be a 1, and this pin to be a 1, and everything else to be zeros.
Yeah, I know how to do 1 digit, but how to do 2 digits? When your binary in your binary code, it's changed 1 to 0. It's supposed to be changed a lot of pins in the
That's correct.
segment.
So you have to figure out why we have a ROM component in this design.
Keeps memory.
Remember the ROM? Well, you kind of missed that part. You missed part of the music box presentation. Yeah.
And do you have record for your lecture right now?
I believe it is still being recorded. Let me check. Yep, it is still being recorded. So I have the full recording from the YouTube presentation.
Okay.
Okay. So the ROM is a very important piece. Okay, the ROM is the drum, and then the register and the adder is the mechanism to make the drum rotate. Okay, so you kind of have to think about what it is and how to make it tick. Okay, how to make it work. Okay. So are there any questions about the 7-segment display component or any of the other components? Yes.
Okay, so you said it's a music box. Like, do we pick a song that we're supposed to represent, or are we just gonna go 1?
No,
2,
you just
3,
from
4,
you just
5,
go from
6,
0
7,
to
8, 9.
0 to 9, 0 to 9, 0 to 9.
So it's really like it's a 0 to 9 counter.
Yes.
Okay.
Yeah, because I don't think the output has a buzzer. No, it has
I
no
thought it's,
buzzer.
like, represent musical notes as numbers or some crazy crap like that.
Well, it has the mechanism of a music box, but it displays instead of plays a sound.
Okay.
So are these how loops work?
What do you mean by loops?
Like when you use a loop in like C++?
Oh, no. The loops are a little bit more complicated because with a loop there's a condition to exit. So this has no exit condition. It just keeps going. The same pattern keeps going forever. Yep.
So how do we use the register?
How to use a register? Okay, let me just place the very last component because I looking at the input-output thing. I forgot one thing, which is the button. Okay, so the button is this one here. Okay, so I'll hook up the button to the display just to show you guys what a button does and how it is different from, let's say, an input pin. Okay, so a button is basically something that is interactive. If you click it, it is a 1. If you release it, it is a 0. See? Yay! Okay, so make sure that you have these components in your design. Okay, so the one thing that we haven't really explained yet is the register. So the register is really a D flip-flop, edge-sensitive D flip-flop that has a certain width. So let's take a look at the register at this point. So the first thing we want to do is to look at the attributes or properties of a register. You can select the number of bits that you want to store in the register. You can make the trigger rising edge, falling edge, high level, or low level. I will just keep it as rising edge, okay, so there's no need to change that. If you prefer, you can change the label and make it, let's say, loop counter or, drum counter or something like that, but there's no need to label the register. And the font is really just, changing the font of the display itself. So the register doesn't really, looking at the properties, that's just what it's going to tell you. So for the rest, what you want to do is to go to the library reference again and go to the memory library and look at a register and see how it describes the behavior as well as the pins. So the register stores a single multi-bit value which is displayed in hexadecimal within its rectangle. So that's what this 00 is about. And it is emitted, the output is emitted on this Q here. Okay, so the Q port is the output of the register, much like Q is the output of our D flip-flop. Are we okay with that? Okay. So Q is the output, D is the input. Okay. The reset pin, can reset the register value to all zeros, okay, simultaneously. And it doesn't even matter whether your clock is low, the clock is high, or it's transitioning. When you assert or when the reset pin is a 1, the content of the register is going to be reset to 0 right away. Okay, so that line is actually level sensitive and not edge sensitive. So of all the pins, we have just explained the output. Q is always outputting. There's no way to turn it off. Okay, so it's always going to output something. D is the input. In other words, that's how you specify what is the new content, what should become the new content of the register. The enable is the only one that we haven't talked about in the edge-sensitive D flip-flop that we talked about the other day. So the enable pin basically says if the enable pin is a 0, you can be clocking all day long and nothing is going to happen. So in order to store new content in a register, in this particular case, you need two things to happen. You need the enable to be a 1, and then the clock has to see a 0 to 1 transition. Then the register will remember whatever is presented in the D port, which is the input port. But the output Q will update as immediately as soon as there's a rising clock and the enable is 1. The output will change to the new content of the register immediately. So is that okay? Are there any questions about the behavior of a register? No questions so far? Okay. So we'll play with it a little bit. Okay, I'll play with this on a separate circuit. Okay. So getting back to Logic Sim, are there any questions? Yep, go ahead.
Why do we need the register?
Why do we need a register? Because you have to.
What it can do that the ROM can't in this scenario?
Well, the ROM can store many different bit patterns. Okay, and you need to display different digits, right? Somebody has to know how to display a 0. Somebody has to know how to display a 1 and a 2 and a 3 and so on. And that's the job of the ROM. Okay, because you can say, okay, I need this many bits in the ROM to store all these different configurations of the 7-segment display. But what is going to control which location on the ROM is being used at this point? In other words, what is controlling the position of the drum? The register is. So you're using the register to control the rotation of the drum so that you have control over which part of the drum is contacting the comb at any particular time. The register's job is to do that. Yep.
So the register is technically the address bus?
It is related to the address bus. You have to figure out a way to connect the register to the address bus. Okay? Now the adder, on the other hand, is the mechanism to rotate. Okay? Yep.
How do you, I'm just trying to figure out how you would figure out in Logisim with these components how you've reached your maximum value to reset.
Well, use an OR gate, and I really said the OR gate has to do with resetting the register. So now you have to think about, okay, so what are the inputs into that OR gate? So just kind of think in that line. Use that line of thinking. We know one of the inputs already.
Yes.
Okay, that one is actually pretty clear. But where's the other one coming from? You have to kind of think about that. All right, so I'm going to start a new design here, and just to show you guys how to use a register. Okay, so we'll pick out a register again. So we go to memory, pick out a register right here. Okay, and I'm going to magnify the design here because we have space. We can just make it a little bigger. And then I'll just give you all the control pins. Okay, so this is going to be D. That's going to be enable. That's going to be the reset line. This is going to be the clock line. And that's going to be the output. Okay, so I need to change the width of these pins a little bit, making sure that the input pin is 8-bit wide, the output pin is also 8-bit wide. So these two are fairly easy to hook up. Okay, so just straight in and straight out here. Okay, input pin, output pin. Okay, this one is going to go to my enable. Okay. Now the enable pin in your design, it really doesn't serve any particular purpose, so you can have it enabled all the time. Okay, if you choose to.
So we can just connect a constant to it?
Yeah, if you want to. I mean, yeah. Oops. Okay, I want to get rid of that. Okay, this goes into the clock line. So you have to think about how to use the clock signal in your design. So everything that I do here is really just for the purposes of demonstration. So in your design, you don't want to have this many input pins. In fact, your design should have 0 input pins. There should be no input pins like these whatsoever, and there should be no output pins whatsoever either. Is that making any sense? Because you got a button, okay? You got a button, you have a clock pin. Those are not input pins, okay? They replace the input pins because they serve kind of the same purpose, but you do not have input pins. So now we have a whole design already done. The first thing you notice is if you want to test your design, you can actually force the content of a register to something. So once you're in the simulation mode, you can click on a register, and once you see the 2 hexadecimal digits in a register to be in a red circle, that means whatever you type on the keyboard becomes the new content of the register, like right away. So I'll just pick. Okay, if I want the output to be 1001 1100, what should I put in as the hexadecimal digit? Let me just put it on the whiteboard so that we can take a look. I want the output to be 1001 1100. How do I do this conversion into hexadecimal numbers? Okay, so okay, first of all, you chop this number in binary into chunks of 4 bits, okay? But you do the chopping from the right-hand side. Do not do it from the left-hand side. In this case, it doesn't matter because we only have exactly 8 digits. But if you have less than a multiple of 4 digits, it does matter which end you start, okay? So you always start from the right-hand side. This is one chunk, this is one chunk, okay? So for each chunk, look up the table that we talked about some time ago. If you do not remember what table we are talking about, watch that video again. Okay, I'm hoping some of you have already written that table on a piece of paper alongside with your notes. Okay, so this is C in hexadecimal, and this is just 9 in hexadecimal. So this number in hexadecimal is 9C. Okay, so let's see whether that is the case or not. I just typed 9C on the keyboard. And you can see the output pin is reflecting exactly that bit pattern, which is 1001 1100. Okay, great. Okay, so you can inject content into a register if you want to. If I want to reset this whole thing, I just exercise the reset pin, which is this one here. So turn it into a 1 will automatically reset the content, and then I have to make sure that it doesn't remain as a 1 because otherwise I won't be able to change the content in the inside. Okay, so now I want to specify a new content by using the clock pin, the enable pin, and also the input pin of the register. So let's say this time I want a new pattern to be okay, E6. Okay, so how do I specify E6 in hexadecimal? This time it's exactly the opposite process. So you look at each hexadecimal digit, and then you look up the table and say, oh, 6 is represented by these 4 bits, and E is represented by those 4 bits. It's really just a table lookup. Once you have the table, you just look it up. What is 6 as a 4-bit number? 0, 1, 1, 0. Okay, very good. How about E? 1110. Okay, that's right. 1110 because F is 1111. E being 1 less than F is just 1110. Okay, very good. So we specify this pattern as the input. So now we flip some of these bits here. We got 1110 and 0110. Nothing happens to the register because there are 2 things that need to happen when you want to update the storage of a register. First of all, okay, just clocking it won't help. See, I can clock it all day long, nothing happens because this one also has an enable pin. Okay, for those of you, I'm not sure whether some of you would maybe disturbed by these terms, but if you look at this as a gun, okay, if anyone is not comfortable, let me know right away, and I won't use that analogy. Is anyone not comfortable? Okay, you can let me know like after class by email, or you can send me an email right away. I will check my phone right away. Okay, but if anyone is not comfortable, let me know. Enable is safety. Okay, so when the safety is on, it doesn't matter whether you pull the trigger or not. Nothing is going to happen. Okay, so the enable is your safety. And then the rising edge thing, which is the clock line, which is the one with the little kind of triangle here, that's your trigger. So in order to actually make the change, you need to have the safety off, and then you pull the trigger. Okay? Now, the trigger is actually a very good analogy, because a trigger is an edge-sensitive device, and it's only sensitive on one edge, but not the other edge. In other words, when you pull a trigger, the gun will fire once. But when you release the trigger, does it fire again? No. So it's a rising edge trigger, not a falling edge trigger. Yeah. I'm pretty sure some lawmaker will make a law and say that you cannot use guns as an analogy in any class. So first of all we release the safety, and then we pull the trigger, and we got the content updated. So after you updated the content, now in general, after you update the content, most of the time you want to disable the register again, just so that it doesn't get accidentally updated again when you when you have the clock having a rising edge. But in your design, it doesn't really matter because there's nothing else that can be interfering with the update of your register. So you can leave the enable on all the time in your design in this homework. Yep.
What if you connected 2 wires so it only enables when you're clocking it?
You mean having both connected to the same pin?
Yeah.
That would not be a very preferred way to do it. Okay, so let me explain to the class what you meant. Okay, so what you meant is to get rid of one of these pins and then have both of these wires connected to one single pin.
Will that be better than a constant?
You can do it with a constant. Yep, you can do it. You can connect the enable pin to a constant that is always on in your design for this homework. Yes.
But don't we need both of our constants for the adder?
You can use the same constant for various things because you can use any number of wires. So as long as it's the same constant, it'll be fine. Now, you also have a multi-bit constant, okay? I just gave away, a little part of your program. Yeah, so you have a multi-bit constant. By using a splitter but you only got one splitter, so you cannot do it that way. Never mind. Scratch that. Because if you can have any number of splitters, you can split that one constant, and because that constant is going to have zeros and ones, then you get zeros and ones. And then you can connect those zeros and ones however you want, throughout the whole design. But since you only have one splitter, you cannot waste that splitter on this. The splitter has one particular place to go, okay? Because the output of your ROM is one single port, but the 7-segment display has 8 individual pins, and each one is one single bit. You are wasting your splitter for that purpose. And something else, okay? I'm gonna say there's something else that you're gonna use the splitter for, but I'm not gonna say it because this is really the only tricky part of this design, so I'm not gonna give that away. As I talked about in the first class, if the homework assignment does not stump you even a little bit, I'm not doing my job right. So you have to be stumped a little bit, yes?
So what happens if you connect clock pin and enable pin?
Together? Okay, that's a good question, so I will answer that question because it is a very good question. So the question is, what if I get rid of this and have these 2 pins connected to the same thing? And in theory, it seems to be doing the same thing because every time I clock high, the enable is automatically high.
Yeah.
But now there's a raise condition. Okay, the raise condition is basically saying, okay, internal to the register, okay, is it going to respond to the enable pin faster than it responds to the clock pin or the other way around? And we never know because you're not designing the inside of the register. So inside the register, if the circuitry to deal with the enable is slower than the circuitry that deals with the clock line, then it would not be the same as having a separate pin that controls the enable. On the other hand, if it is, then in this particular design, when you always want it to update whenever you clock, then it will be equivalent. Is that making any sense? So you don't want to put yourself into any situation where a hardware raise condition can change the outcome of what you're doing. And I'll give you a story after I answer George's question.
I think you're about to answer.
Oh, okay. So this is back in the days when I was still working as a software engineer writing firmware. Okay, so remember, the firmware part of a computer, any computer, is the part that starts working as soon as you power up this computer, right? And at that time, you don't have any RAM because you don't know where the RAM is located. You have to basically find where RAM is located by exercising the chip select lines and go to different memory locations and see if you can store something and get it back. Because depending on how the hardware is configured, the RAM chip can be somewhere, but you have to find out where it is. And this is also the part where you cannot GDB because there's nothing up and running yet. Okay, so you cannot connect to anything to help you with debugging the design. Okay, so put yourself in this scenario. You are a software engineer working on a particular product using a processor that has been used for at least 8 years. Okay, so this processor has not changed any specification. It has been used for 8 years. And then one day you get a call from production or from marketing, and they say, "Holy XYZ, okay." All the new boards that we sent out stopped working. Okay, and then the first question you would probably ask as a software engineer is to put the blame on somebody else. It's like, did we change the design in hardware? No, nobody made any changes. Okay, so you cannot change the hardware engineers. So now you try to blame the manufacturing people. Did you guys change any parts on the circuit board? Did you change any capacitor? Anything like that? And they say no. You go like, okay, well, that's a tough problem, right? But then you can always say, but I didn't change my software either, so it's not my problem either, so I'm just going to pass the buck on to somebody else. Okay, screw the customers, we don't care, right? But being inquisitive and curious, I had to say, I'll take a look. I had to say that. So I took on this project. And what I found was there was one minor change. Okay, so the chip, remains exactly the same, but they changed the manufacturing process of the chip, the processor chip that had been used for 8 years. At that time, we had been using that chip for 8 years. But they made a minor change. There's a minor revision that says that they changed the die size, the transistor size, so it's more energy efficient and all the good stuff like that. But then I looked through all the revisions in the specification. Nothing got changed, other than yes, we are now consuming less power. The transistors are smaller, So there should be no change of behavior when it comes to what a program should do. Okay, we are still clocking it at the same speed, and nothing has changed. So that was really interesting. It's also more interesting when you have a 6'5" football player marketing manager standing behind you the whole time and say, "Jack, when is it going to be done?" So I had to tell him, I have to give him the only answer that I could give him. It's, Dan, it's going to be done when it's done.
Yeah.
And you can probably imagine how the football player took that as an answer. It's like, so he was the marketing manager, and then the sales manager had to step in and say, "Dan, leave Tag alone. If you don't leave him alone, it will take even longer for the problem to be solved." So he had to walk away.
Yeah.
So anyhow, so when I analyzed the code, I was going through the code with a fine-tooth comb. And this reminds me, it pops up in my mind, a scene from Spaceballs.
We're coming in the desert.
Yes. So I had to go through the code with a fine-tooth comb, like the stormtroopers. And I couldn't find anything that was really suspicious except for one little thing. In the software manual, it specifically say that, okay, this is a 16-bit register, but since it's an 8-bit architecture, you can only change 8-bit at a time, okay? But there's one thing that is quote-unquote a 16-bit register. It controls something that requires 16 bits, basically. So you cannot do it in one single write operation. You have to use 2 write operations to write 16 bits with an 8-bit architecture. So the manually calls for a particular order, write to the lower byte first and write to the higher byte, okay? And then when I looked at code, it was doing exactly the opposite. It wrote to the higher byte first and then the lower byte. Okay? But that code had been working for 8 years. Remember, we haven't changed the code for 8 years and had been working all this time.
It's not a big change.
It's not a big change, but it had to do with an internal mechanism to make sure that we don't have a raise condition. When you write to the low byte first and then write to the high byte, there's an internal lock mechanism to say, do not update anything until the high byte is written to. When you do it the opposite way, then it doesn't protect itself from the raise condition anymore. So it was a matter of a raise condition. Raise as in R-A-C-E, raise, raise. So when they changed the die size, it changed the timing of some internal circuitry just enough that something that apparently was working did not work anymore. That was it. That was like 2 lines of code of the entire thing, and that was the whole bug. That was the bug. It took me 2 days or so to find that bug.
How do you figure something
marketing
out like that? How did the light just go over your head? Oh, I need to check this.
Oh, there's no other way to do it, because when you encounter problems like this, and nothing has changed, then you have to basically just go through the whole thing. It has to be something that has been overlooked.
How long was that specification?
Hmm?
How big was that specification that you had to? Because you basically just decided to read.
Yeah. Oh, you can look it up. The chip is probably still manufactured today for some really odd reasons. It was the Zilog Z180 chip, and then you can just look up the data sheet. The data sheet is basically what would tell you about the processor and how to use it. Okay.
Megabytes. Wow.
Yeah,
Pages.
Yep.
Pages.
It's not too bad. It's only 84 pages.
Side question. Does this PDF reader have tabs?
Huh?
Does this PDF reader have tabs? It's not like it's just a side Linux question.
Tabs?
Yeah, like can you open up multiple PDFs within the same window?
I do not think so. Control T, no. I don't think there are any tabs here. But it's one of the control registers. I cannot remember exactly which one, and the writing of those registers has to be in a particular order. And the one that was in the firmware was exactly the opposite, and that broke it. But for many years, because the raise condition was favoring the wrong code, the bug was masked. But when they changed the die size, it changed the timing, the internal timing of the circuitry, and then the problem surfaced. So that's kind of why, when you asked that question, I had to say, well, okay, in some cases it looks like it is working properly, but it may be masked, a masked problem that will surface later on. So do not do that. It's not a good approach. But it was a good question. Yes.
So now, would that be considered an actual problem in the code?
Yes, because the code is not following the specifications of the chip.
The code was fault the entire time. It was just never.
Okay.
Yeah, it was just
Okay.
masked
Yeah,
by the.
it was like
timing.
something else kind of just
So
fixed the problem.
So
right?
the,
But the problem was existing.
Yeah, I cannot remember which register, but it has to be a register with a low byte and a high byte. It could be a timer register because you can see that this one has a low and a high. And in the software or in the specification, they probably have somewhere that would say, okay, you have to change the low one and then the high one, or the vice versa. There has to be a particular order because they don't want it to latch until both registers are specified. So it's one of those things, you just kind of look at. When I found the problem, I was really kind of satisfied because I did this out of curiosity more than anything else, and so I found a bug. I found out why it was not behaving correctly.
So
Yep.
Were you the one who wrote the bug?
No. The person who wrote the bug in had left the company for years already at the time. But it's regardless of who put the bug in. My thing is just I want to find out why it is doing it, not so much who wrote the bug. Yep.
Was the code at least readable?
It's all assembly code, assembly language code, using the Zilog architecture. So to me, it was readable. I'll put it that way. To me, it was readable. And that's also why I teach this class, assembly language programming, because my background is dealing with a lot of assembly code. Yep.
So what ended up being the
What solution?
yeah? What did you just change your
Flip it
test?
to-
What was your test? What did you change the test?
I changed the ordering of the update of those two registers.
Also from
Just
high to
transfer the
low,
condition.
from low to high to high to low.
Yeah.
Okay.
Yep. And then we have to collect all the boards out there because the customers do not have any way to update the flash in the field. So they have to take all those back. We have to reflash, but that's a problem that they cannot. There's no way to get around that one. Yeah. All right. So
Just having a big recall.
Yeah, that's a huge.
well, it wasn't too bad. They caught it fairly early, so they stopped all the shipment of stuff that has not been shipped yet. Because the problem was very deterministic. It just did not work.
Yeah.
The worst kind of problem are the ones that are kind of like, it works sometimes and not work other time. It's like temperature dependent, because semiconductor can be temperature dependent. So those are the worst problems because some works, some doesn't work, some will work for half a year and then stop working altogether. Those are the problems. And with embedded systems, you end up with a lot of problems like that if you don't program carefully. Because of reentrancy, because you basically have things that are happening at the same time. You have interrupts and stuff like that. So the interaction between the code corresponding to interrupts and your actual normal code, if that interaction is faulty, the symptoms because of the same problem can be very different every single time, and there's no telling how frequently it's going to occur. So those problems are very tough to fix because, first of all, you cannot reproduce the problems. It's not like, okay, here's a test case. Every single time you use the same test case, the program responds exactly the same way. Those are easy problems because it behaves the same way every single time. But if you have problems where the symptom appears to be completely different every single time, and there's no predictability as to when the symptoms can happen, then you have a much tougher problem because you cannot capture the case. Yep. So that's my previous job before I started teaching here. It was fun. Then they promoted me to Director of Software Development, which I did not. I kind of declined that title. I said, okay, I'm a software group leader, kind of more like a platoon leader instead of a rear general. I'm the first one to charge. All right, so are there any questions related to the homework assignment? No questions?
When is it due?
It's due in a week, so most of the homework assignments are due in a week. Any questions?
Probably have some Tuesday.
I would start working on it in the lab time today,
Mhm.
so that if you have encountered, if when you play with it and you see a particular question, then you can ask me during the lab time. If not, definitely work on this over the weekend, so that next Tuesday will be your second chance and last chance to ask questions during lab time, not counting my office hours. All right. All right, so now that we're done with these topics, let's go ahead and talk about multiplication. Probably we don't have time for division, but we can talk about multiplication in binary in a circuitry. Okay? So now the question is, how do you multiply numbers in binary? But let's do it by hand first, okay? Because if I cannot do this by hand, I have no chance of making the circuitry to get it done, okay? So first thing is to do it in, let's see if I can get my document camera to work here, because that would be even better. It's the same way that you do multiplication, but it's easier in base 10. Oh, it does work. All right. Well, the other day I was trying to get this to work. Unfortunately, it wasn't working very well. Okay, so let me do autofocus on it. Okay, it's a little bit blurry because I did not turn on the LED light. The other day, at the moment I tried to turn on the LED light, it stopped working. I think it might have to do with a current issue. It just cannot supply the current. I'll give it one more try today. If it doesn't work, then I'll just go back to the whiteboard. Okay. I need to put an inline switch with the LED light. Next project. There we go. Oop. Okay. It's not even. The weight distribution is not good. Is that better?
Better.
Okay, still has a little bit of a keystone distortion. Okay, well, I'm not too picky about that. Okay. All right, so let's go ahead and do some addition. Multiplication by hand first. Okay, so we're going to multiply. Okay, let's say 1 0 0 1 in binary to 0 1 0 1 in binary. Okay, and all of these are binary numbers. Okay, so what do? Well, it's the same way that you do multiplication in any base, okay? So you basically just say, okay, is this multiplying anything to the first number? Nope. There's a 1 here, okay? So let's go ahead and this is the way I was taught to do. I know some of you were taught the opposite way, but it's still the same idea, okay? It is still exactly the same idea. Huh?
So you're just going from left to right.
Yeah, I go from left to right on the bottom row. Some people go from right to left, but it's the same idea. It doesn't really matter. Okay, and then we have a 1 here, so we have a 1 0 0 1 over here, and then you just add these two numbers together. We have a 1 here, 0 1 1 0 1 over here. Okay. So the question is, okay, but is the result correct? Okay, so we can figure it out because this is representing the value 9. This is representing the value 5. So the question is this 45? So let's check it out. It's 1 plus 4 plus 8, no 16, but a 32. So we have, we have 45. So it does work. Okay. Is that okay?
How'd you get those numbers? I don't get how you got 1 0 0 1 1 0 0 1 like with two different things that you were multiplying together.
Yeah, why did you do that?
Did you multiply it from like top to bottom, like the 1 0
Okay. As I said, my order of doing it may be opposite to what you guys are used to. So I think that's what threw you guys off.
Every 1 you put 1 0 0 1?
Okay, let's look at this from a different perspective, and I'll use exactly the same two numbers. So we are multiplying this number by this number. Is that okay? Does everybody see that this is exactly the same multiplication, but shown a little bit differently? Is that okay? All right. So what I'll do next is to look at the first number, 1001 in base 2, still as a whole, but I will look at the second number as 100 in base 2 plus 1 in base 2. Would that work? I just drop out all the zeros because they're not really important. So I just break the whole thing down and say, okay, it's 101 in base 2, but 101 in base 2 is 100 plus 1 in base 2. Can we buy this?
Yes.
Okay. Then we use the distributive law of multiplication. So now we end up with 1001 in base 2 times 100 in base 2 plus 1001 in base 2 times 1 in base 2. Would that work?
Yeah.
Are you guys all buying this?
Yeah.
Okay. So how do we do this in binary? How do we perform this particular multiplication? You shift by 2 digits, right? Just like the same way you would do it in base 10.
So
There's no difference.
100.
So it becomes 100100 in base 2. These 2 extra zeros come from these two zeros. Would that work? Is that okay? Because 100 in base 2 is representing the quantity of 2 to the power of 2. So we are multiplying the quantity 1001 by 2 to the power of 2.
Or we're increasing it by 2 powers of 2.
Then because each digit is representing a power of 2, so we're just shifting all the digits to the left-hand side, because all you're doing is to say, okay, you used to be in charge of the 2 to the power of 0, now you're in charge of 2 to the power of 2. Right?
Yeah.
That's what we're doing. That's why bit shifting works. Okay? The other one is easy because there's no bit shifting involved. It is just itself like that. Is that okay? Does that resemble anything from the previous page? Put this over here. Perform the addition like that.
101.
Yep. Same result.
Yeah. What is that?
Yep.
Where I'm not following is over there where you split up that second number into 100, 2 plus 1.
No, that's 4 plus 1.
Yeah, what'd you do that for?
That's 4 plus 1.
You mean this part here?
Yeah, so what you did is you dropped that first 0 and then you...
I dropped all the zeros because the zeros are representing, there is none of these powers of 2. Well, if there's none, then it won't affect the actual result of the multiplication.
Okay, and then all the other digits you do them one at a time.
Yeah, I just write one of them at a time, but with all the zeros, so that I know how many positions I have to shift.
Okay.
I'm still confused on the second line, how you split them up. Can you please go over it?
You mean from here to here?
Yes, yes.
He did distribution.
Sure.
Right?
Right.
So A is this guy, B is this guy, C is, okay, I shouldn't have drawn it that way, that guy.
Okay.
Okay.
So-
Algebra. Yes.
For the addition part, do you want us to use the previous adder we had?
Sorry?
For the addition part, you want
Yeah.
to use the adder we built
Yeah,
earlier?
you can just use an adder. Yeah. So, but that's the principle of multiplication. Okay. So but this is a very specific case of multiplication. So now the question is, what if this is not like this? Okay. So I'm gonna turn to the next page and say, okay, what if this is more general? In other words, what if I am representing the bits as just alphabets? So we are multiplying A, B, C, D by E, F, G, H. Okay, and these are all binary numbers. In other words, A, B, C, D, each one is a binary digit, and E, F, G, H, each one is also just a digit. Okay, so how do we do this?
Oh. Never mind. I'm thinking.
Well, then it becomes A, 0, 0. Okay, I take it back. It's A, B, C, D times E, 0, 0, 0, right? plus A, B, C, D times F 0, 0. Okay, whatever that thing is, add A, B, C, D times G 0. Whatever that sum is, add it to A, B, C, D times H, because H is the least significant bit, and then the final sum is the answer. Are we doing okay so far? Hold on a second here, Tag. This seems to be the same way that we do base 10 multiplication. It really is. Yep.
So if we had 3 ones, we're going to have 3 times where we're...
Yes, but this is a very general case. So for E, F, G, H, if one bit is a 0, you can still do this. Okay, there's no problem if G is a 0. It simply means that it doesn't really do anything because A, B, C, D times 0, 0 is just 0. But it still applies because you can still do the multiplication here, except it doesn't do anything actually productive. Are we doing okay so far? But the best part of binary multiplication is for each individual term, okay? For the term like this, this, and this here, there's no actual multiplication because each one of E, F, G, H can only be either a 1 or a 0. So it's either there and shift the position or it's not there at all. So that makes it a lot easier to deal with compared to base 10 multiplication. Is that making any sense?
Mathematics becomes so much easier with binary.
Yes. Well, that has always been what I claim. You know, if I were a politician, that would be my platform. Let's change to base 2 and base 16. And then we'll force this standard on the rest of the book.
Yeah.
So it's, the time is almost noon, that'd be what? Time is almost C?
Yeah.
Time is almost C?
Yeah, we would have a clock of like hexadecimal.
Yep. Yep. We'll change the way we represent time and all that stuff. Yes. Okay. So we're running out of time today. We have to leave the classroom so the next class can come in. So we'll continue the hardware multiplier discussion on next Tuesday. Okay. So for those of you who are truly curious, okay, try to put this together. Okay. And if you cannot, that means we're missing one single component that is really crucial to this implementation.
Are we only doing 4x4?
Yeah, you can just do 4x4, or for simplicity, do a 3x3. It's the same principle.
I don't know, but if we're base 16 clock, your last bit would be...
Well, that would assume